Okay guys, we have pretty much done everything now to do with forces. The only things that we'll be adding in on this topic, as I was just saying, is where they have things like one particle hits the floor and how does it move in the subsequent motion. And that's because there's quite a few things that happen, and I definitely will make sure we do that, and we'll probably do that as one of our very, very last lessons on mechanics as a bit of a revision lesson slash adding in that new kind of skill. But there's no reason why you couldn't do it now. You probably can do it already if you could do those questions from year 12. Who knows, we might come across one when we're doing some of our practice in today's lesson anyway. So we're going to do connected particles on slopes, connected particles in all, not just ones that look like this. One of the questions I'm going to set you later on looks like this kind of thing. We talked about this before, didn't we? We talked about the different situations with connected particles and how friction we can now take into account for all of these things. So we're really revisiting those ideas that we've got. The diagram has already been drawn for us, but I'm still going to read through what we've got. Two particles P and Q of masses 5 kilograms and 10 kilograms respectively are connected by a light inextensible string. The string passes over a small smooth pulley which is fixed at the top of a rough inclined plane. That's the first time we're coming across it now with a rough part. P rests on the inclined plane and Q hangs on the edge of the plane with the string vertical and taut. Sometimes at this point in the question it says that Q is not in contact with the plane, because if it was in contact with the plane there would be friction that would be happening there. So we presume that it's just hanging freely, it's not really touching the plane. The plane is inclined to the horizontal at an angle alpha where tan alpha is 0.75. As soon as you see that, we should be thinking of some other things, as shown in the diagram. The coefficient of friction between P and the plane is 0.2. The system is released from rest. Find the acceleration of the system and the tension in the string. Right. I'm going to just quickly deal with this thing first of all. If tan alpha is 0.75, what do we also want to find out? Sine alpha and cos alpha. And we know 0.75 is the same as 3/4. So it's tan is 3/4, opposite over adjacent. So sine alpha is 3/5, and then cos alpha is 4/5. Just because we know we're going to need to be using that throughout the question, it's always good to kind of start off with that bit that we have there. Now, it doesn't tell us what's going to happen in this scenario. But does anyone have any predictions of what they think is going to happen here? I think Q is going to accelerate downwards. Why do you think Q will accelerate downwards? It has it's a much greater mass. It's got like quite a lot greater mass. Usually in the question, it would say something like maybe part C or D. It says Q hits the floor and Q is 2 meters above the ground. Find out how long it takes for P to move up the slope. So it would usually reveal in the question what's going to happen. So that actually tells us we think this one is going to be moving downwards, which obviously means this one is going to be moving up the slope. So all we really need to do now is just add on the diagrams to the forces, and we proceed as we did before, apart from this time we have friction included as well. So let's just concentrate on this Q particle to begin with. Imagine that you were that particle. What do you feel? Tension. Which way? Up. So tension up and weight down. That's what it feels like if you are that particle. If you are the particle P, which is on the slope, you feel a few things. You feel your weight pulling you down. What else do you feel? You feel friction going down, so we're going to have mu r going down. Anything else? You feel the normal contact. You feel the surface pushing into you, and the tension going up the slope, or yeah, because it feels like it's pulling you upwards, right? Now, when I look at that diagram, why is the tension equal in both sides of the string? What modelling assumption? Inextensible is to do with it. Light is because it's throughout the entire string. But why is the tension equal on this side and this side? Smooth pulley. Smooth pulley is the thing that means it's equal on both sides. Because if it was a rough pulley, it might be tighter on one side because the pulley might snag it. Okay. No, you just have to say smooth pulley, okay? The tension being equal throughout the string is what Shah had said about it being a light string. Do you remember how did I try and explain the idea of what would happen if a string was, it wasn't light, what that would do? Do you remember what I used as an example? Yeah, if you had the top of a string, if you had something hanging down, if it was a big heavy rope, the top of the string is having to support whatever's at the bottom and the whole rope, whereas the bottom of the string is just supporting whatever's at the bottom. So there'd be different tension. It would actually get more tension as you get to the top. Okay, so all we need to do now is resolve some forces. So this 5G needs to split, 5G cos alpha, we're running out of space, and 5G sine alpha. Now, this is different to what we did before. I think when we did these scenarios recently, what was the main difference between this scenario and that scenario? No friction, and there was another difference as well, I think.
Was it like not upper ramp?
We did one of them a couple of lessons ago, not upper ramp. It's not important if you can't remember this, what the difference is, but the difference was they were static. This is not static, this is dynamic. So we won't be using the forces all being in equilibrium this time, will we? We'll be having to use, because it is dynamic, we're going to have to use more of F equals ma, okay? So we usually find out these things which are called equations of motion. When you do F equals ma, it's actually called an equation of motion. So if they ever ask you to say, find an equation of motion for P, you might be like, what does that mean? I don't know what this is. But it just means do F equals ma for that particular particle that you've got there. It just means do F equals ma. It doesn't even need to be simplified for that kind of thing. So I'm going to start off. I'm going to have a look at doing F equals ma downwards. And I'm going to do that for the Q particle, right? And the Q particle, I know it's annoying because I've got the acceleration kind of hidden behind this bit. For the Q particle, it's accelerating downwards. So what's the resultant force for it?
10g minus t.
So you get 10g minus t equals 10a. Okay, good. And now we're going to do F equals ma going up the slope for P particle, right? Now, I may need to draw an extra diagram for the P particle to make it a bit easier. We've got R, we've got T, we've got 5G cos alpha, we've got mu R, and we've got 5G sine alpha. We're going to have T minus mu R minus 5G sine alpha equals 5A, okay? Now, I may pause on that because I feel like there's an awful lot of unknown things there, isn't there? I had T, I had mu, I had R, I had so many things that were unknown. So maybe there's something we should have done before we even went in with the equation of motion. Yeah, I think we perhaps should have looked over at this side for a bit, and we probably should have done our normal thing that we do with friction, where we should, okay, say, well, why don't we actually, for this P particle, why don't we resolve in that direction and say that R is 5G cos alpha? What is 5G times cos alpha?
5G times 4.
Which is
4G cos alpha.
just 4G. Don't need the cos alpha anymore. So we just get that R is 4G. Now we can work out what the mu R bit is, because mu is 0.2 and R is 4G, and 0.2 times 4G is 0.8G. So that little bit of side working, it's not like an essay where in maths you need to be, like in English where you'd need to like write the whole thing out in a particular order. Maths we can actually be, as long as we keep our page sort of organised, you can do things in different areas. You can jump out of what you were doing. Like here when Ahmed gave me the correct equation, he might have then said, oh, actually, you know what, I'm going to do this first, and then I'm going to come back to this. However you want to move around that page, okay? So we're now going to do F equals ma for P, and that was, using this diagram, maybe it's even easier, T minus mu R minus 5G sine alpha. So we've got T minus mu R minus 5G sine alpha equals the mass times the acceleration, okay? And now we can substitute everything in. So that's T minus 0.8G minus 5G sine alpha 3/5, which is just going to be a 3G. So you get T minus 3.8G equals 5A. I'll just give you a chance to write some of these bits down because these are very important examples for you to keep track of. So what have we kind of like come across now? Can anybody spot what it is? Yeah, it's going to be simultaneous equations because remember, they want you to think about the acceleration and tension. Well, this one has got acceleration and tension. Remember, g is just a number. This one has also got acceleration and tension. And that's our equation of motion for the q particle. And this is our equation of motion for the p particle. And we just want to kind of combine those equations together to find out what a and t are. Now, I don't care how you solve these simultaneous equations. However, there is always going to be this particular method that works for this one that we have. And can anybody spot what's a good method to do with these two highlighted equations that will always help you solve them? Yeah, if you add these equations together, what happens? The t's cancel. So that's always a good way of doing it. But I remember when I did these problems at your age, I always liked making t the subject just because that's my favourite way of solving them. So however you want to do them, you do them. But it's only now as a teacher I realise you can always add these together and they're always going to cancel because one of them has got the tension in a positive direction and one of them the tension is in a negative direction. So I'm going to add, and I'm going to call this one number 1 and this one number 2. I'm going to add number 1 and number 2 together. So when I add these bits, just be really careful when you add them. You're going to get 10g minus 3.8g. And that will be equal to 15a. 10 minus 3.8 is 6.2, I think. So 6.2g divided by 15 is equal to the acceleration. So the acceleration is 4.050, or we could just say 4.1. Today I'm going to use two significant figures because why not? I've used that. But there's a health warning here. We're going to need to use this value of a to find out the value of t. So don't use this value of a to find out the value of t. Use this value of a. Why am I saying this? To get the accurate one. If you use a rounded version and then you do more maths on it, the rounding is going to get more and more inaccurate as you go. So to now find out the value of t, well, I don't know, which one do you think is easier to use, 1 or 2? The second one is easier because it's already got t as positive. So using 2, I can see that t is equal to 5a plus 3.8g. But you know, if you've just got it in your calculator anyway, if you haven't cleared the calculator, you're ready just to use the answer button. So we can just say it's that times 5 plus 3.8 times g, and we get 57.49333, or 57 newtons. And as I said today, I'm doing two significant figures, because remember in the exam you can either do 2 or 3, whatever you want to do will work out, okay? Hopefully this doesn't feel actually very overwhelming. Hopefully this just feels like we have really slowly built up these skills that have got us to a stage now where we're just like, this all makes sense. If this doesn't make sense, then I'm sorry, I don't think I've taught it very well. Okay? What I'm going to just, while some of you are writing that down, what would probably happen in the harder versions of these questions is it would say something like Q is 2 meters above the floor and P is further away from the pulley than 2 meters. It's quite far down the slope. And it would say something like, how long does it take for P to come to rest? So Q would hit the floor, but P would have already been traveling at that point. So P would keep moving up the slope even after Q has hit the floor. But after Q has hit the floor, what can you say about the way that P would be traveling up the slope? Would it be going? It would be decelerating because it's no longer got tension in the string because Q isn't moving anymore. So because it's decelerating, you'd have to calculate its deceleration. You have to do lots of SUVAT for that kind of question. But we will leave that for another day. But just you've got the logic and the reasoning skills to be able to just figure it out yourself as well. But I'm not going to be setting you any homework questions or questions like that. Just in case you come across an exam question and you want to know how to do it, please try it out yourself. But I promise you I'll be doing it in a lesson as well. Yeah.
What kind of questions did you say we had to relook at acceleration?
So if there's ever a stage where one of them hits the floor or if the string breaks, then there's no longer any tension. So let's say we were considering this particle P over here. Here is its equation of motion down here. If the string broke, there would be no tension. And so you can clearly see that the acceleration is now going to be a negative acceleration. It's actually going to be slowing down. And that kind of makes sense. If you imagine the string breaking, why would P keep flying up the slope? It would keep going up the slope, but it would be slowing down because of the friction and the weight that would be slowing it down. So when I say there's a new acceleration, it's as simple as going back to your equation of motion, just getting rid of the tension and finding the new acceleration, and then it all just becomes a kind of SUVAT exercise. But it's tricky, so we might do it in a few lessons' time. I might not leave it until the very end, okay? So we've got one more here. And for this one, should we do this together? This one's actually quite simple because I'm really only doing this one to get onto part C of the question. That's the main thing I'm trying to show you with this one. So I might actually go through the beginning bit quite quick, and then we can do lots and lots of practice. The reason this one is simpler is because of this word that I've got here. I couldn't find enough questions with friction, but there are some in the questions. So what we're really aiming for in this question is to look at part C, which goes on to the very last page of your booklet. If you don't want to write this one down, I'm going to be going quite fast anyway, but you're welcome to obviously write this as we go. So we've got one end of a light inextensible string is attached to a block A of mass 2 kilograms. The block A is held at rest on a smooth fixed plane, which is inclined to the horizontal at an angle of 30 degrees. The string lies along the line of greatest slope of the plane and passes over a smooth light fixed pulley. I mean, it's the same old stuff every time, isn't it? The other end of the string is attached to a block of mass 5 kilograms. It's released from rest by modelling the blocks as particles and ignoring air resistance. Show the acceleration of the block B is 4/7 g and find the tension in the string. Okay, so they've told us there's something slightly different here. It's a smooth slope. We can still add in the same forces. Imagining your particle B, there is weight and there is tension. Particle A, the tension feels like it's pulling you up the slope. You've got your weight and you've got your normal reaction. Obviously, though, there's no friction in this particular question, so it's actually pretty simple, this one that we've got here. And the angle is 30 degrees, so I'm going to just very quickly resolve these. So I have my 2g cos 30 and my 2g sine 30 that I have here. We're trying to show that the acceleration is 4/7 g. Any predictions of which way this one's moving? Same as before, yeah? Like this one is a lot heavier, so we think this one is going to be accelerating down. And to be honest with you, most of the time that's what happens, but I just don't want you to think it always happens that way. So we'll do an equation of motion. We'll do F equals ma for B. What's the equation of motion for B? Luke?
Would be 5g take away tension is equal to 5a.
Good. The resultant force downwards, this one is bigger, so it's 5g minus t. If we do F equals ma for A, so maybe we should have done an extra diagram here. I might do it very quickly. R, T, 2g cos 30, 2g sine 30. Tashini, would you be able to tell me what the equation of motion is for that particle? Yeah? Okay, there's a slight mistake in this one. Who can spot what the mistake is? It should be the other way around when you subtract them. Because it's moving up the slope, the resultant force is in that direction. So instead of it being like this, it's going to be the other way around, okay? It's going to be t minus 2g sine 30 equals 2a. And in this case, I'm not bothered about the size of the normal reaction. Why don't I care about the normal reaction? It's not the same as the weight. It's irrelevant. Why is it irrelevant? There's no friction, so I'm not bothered about the normal reaction at all. So I've got equation 1 and equation 2. What am I going to do? Add them together. 1 plus 2, you get 5g minus 2g sine 30 equals 7a. What is 2g sine 30? 1g. So it's just 5g minus g, which is 4g, equals 7a. So you get 4 over 7g is equal to a, which is what we wanted. Okay, nearly there. I'm going to use 2 to find out what t is. So using equation 2, t equals 2a plus 2g sine 30. Well, that's going to be 2 times this, which is 8 over 7g. And sine 30 is a half, so half of 2g is g. 8 over 7g plus g is 15 over 7g newtons, I could have said. Yeah? If it can be kept in terms of g, keep it in terms of g. I've noticed a few people when we've done questions on the board, some people are like desperate to use 9.8. Don't use 9.8 unless it kind of feels appropriate. Here it feels like everything is in terms of g, so we can keep it in terms of g, but let's see what it would have been. It would be 21 or 21 newtons if you actually worked that out, okay? That's the easy part of the question in some ways. We've done this bit now. State how you've used the fact that the string is inextensible in your calculations. So what does inextensible string actually tell me? How have I used that in my calculations? No, when it says it's inextensible, it means that it doesn't stretch. It doesn't mean that it will always have tension in it, because it just means that it doesn't stretch. Good, it means they have the same acceleration. And we used that in our calculation here, because we worked out we were able to do simultaneous equations because we knew they had the same acceleration. So how you've used the fact that the string is inextensible, I've used it both particles have the same acceleration. That's actually how we've used that in this question. Now here comes the main reason that we actually did this question, is it says calculate the magnitude of the force exerted on the pulley by the string. So we've got all of this information here. If you need me to come back to this slide in a second, I can do. But I wanted to just look at this diagram in a little bit more detail of what has happened here. So the thing that we're asking for is what is the force exerted on the pulley by the string. Now, when you look at my new version of the diagram that I've drawn there, what is different about the new version of the diagram? The tension has flipped. Because in this previous version of the diagram, I asked you to imagine that you were a block on a slope, right? And I asked you to imagine that you were a block hanging from a piece of string on a slope. You were like focusing on those two separate things. But part C is asking you to focus on something else. It's asking you to say, what is the force on the pulley? So weirdly enough now, I'm going to ask you to imagine that you were a pulley, okay? And what it should feel like if you were that pulley with a piece of string hanging over your new body, which is just a pulley, is it should feel like the tension in the thing hanging down feels like it is pulling down on you. And from this point, the block that's hanging on the slope feels like it's pulling in that angle on you. And what we're trying to now say is overall, what does that force feel like that it is doing to the pulley? We don't want to describe it as two separate forces. We want to describe it as one single force that there is, okay? Now, I've said what the resultant force is up here, but I'm not going to ask you just to memorize a formula. I want you to think about where this actually comes from. So I'm going to zoom in on this bit of the diagram we've got up here, okay? So here's the pulley. I'm just going to do the pulley as a dot. And we've got tension that's pulling it downwards, and we've got tension that is pulling it acrosswards like this, okay? If I was to draw out the full triangle, this is 90 degrees here, and this is alpha, right? What is this big angle that we've got at the top here if you just think about doing 180? Yeah, so it would be 180 minus 90 minus alpha, which is just 90 minus alpha. So this angle at the top is 90 minus alpha. Now, which direction do you think, when I had that string over my hand just now, which direction does it feel like the overall force is acting? Exactly, like it feels like the overall force is just going downwards. Okay, Amara, hold your hand out. So like this, where does it feel like your arm is having to pull so that it's resisting the pulling force? Like, are you going directly upwards or are you going angled upwards? Pardon?
It's like this way because you're pulling it that way.
So which way is your arm having to resist moving? Yeah, so you're having to pull your arm up. Can you just hold your arm up? You're having to kind of like pull your arm up like that to resist it going downwards like that, okay? So that means, because she was trying to say like, oh yeah, I have to kind of put my arm up at that angle. She was saying I need to put my arm up going like that to stop her arm moving. That must mean that the string is trying to pull it down like that. What can you say about the angle here? It's half of it. So the angle here and here is going to be 90 minus alpha over 2. Now I'm going to draw another diagram because it's already getting a bit messy, okay? So we've got a pulley, and we've got the tension here, and we've got the tension here. And this angle are both 90 minus alpha over 2. Now I'm going to resolve this tension force into two new forces. I'm going to resolve it into one going along, which was into Amara's arm, and then one going up like this. I'm allowed to do that because it's trigonometry, okay? It's what we've done before. And I'm allowed to do it with the other one, which is like this, and then coming along like this. What can you tell me about this and this? The same and opposite. So they cancel each other out, right? They're pulling in like opposite directions, and they must be the same size as each other. So the only ones that we're interested in that was pulling on Amara's arm when I just put the string there is these two arrows that we've got here. Now, again, this isn't what I expect you to do every time you do this. I'm just going to look at one of them for a second. There's the T. This is the one that we're looking for, which is I should have drawn that in red. What is the length of that red one if this is 90 minus alpha over 2? What is this one here? Resolving forces. T cos 90 minus alpha over 2, right? But there's two arrows there. So it's 2t cos 90 minus alpha over 2. There are two of them that are there. We don't ever care about the t sine alpha because this t sine alpha will cancel out with this t sine alpha and it will just completely go. That's why Amara only feels like her arm is pulling up in that way, or the overall force is pulling exactly halfway between them. That's why she only feels that direction, because the sine bits are completely cancelling each other out. So let's answer the question, which is what is the resultant force of the pulley on the string? It will be 2t cos 90 minus alpha over 2, which is 2 times, now I think we worked out that t was 21, didn't we? It was exactly 21. So it's 2 times 21 times the cos of, well, I think in our question it was 30 degrees. So instead of this being alpha, this is 30. We know this whole thing up at the top would have been 60. So each of those is 30. So it becomes 30, because 90 minus 30 over 2 is just 30. But this is the most general way of remembering this. This is the understanding of where this comes from. I don't know who you are. I do know what you're like as mathematicians. Some of you will just be like, great, I'm just going to memorize that. Some of you will be like, every time you might think through the steps of it because you want to like deepen that understanding. I don't mind which one you do. So when you type that in your calculator, you get 42. Cos 30 is, guys, please learn this. So you get 21 root 3, which is whatever that is, which is 36 newtons to two significant figures. So in that question, you imagined being a hanging block, a block on a slope, and you also imagined being a pulley and what it felt like to be a pulley. There is one last thing that I'm going to talk to you about on this question. This force that we had here, and then you can write all of this down. This is the force exerted on the pulley by the string. Who thinks they might be able to describe what that force up there was? It's going to be exactly the same as what we just worked out and in the opposite direction, but what language do you think the question might use to describe that force? Good. This is the normal reaction, or The normal reaction at the pulley. At the pulley caused by the string. And that was what Amara's arm was doing to stop it moving. That was the direction and the size of her force that she was moving her arm with to stop her pulley arm moving in any direction. Okay, so if they ask you something, what is the normal reaction at the pulley? It's the same thing as this. They might ask for the direction. You would all you'd need to do is just do a bit of geometry and work out what's this angle that you've got here, and you'd need to just draw some things out to figure it out, okay? So what you're going to do for me is exercise 7F, you're going to do the odd questions. I actually think you're also going to do question 4. I think I looked through this just at break time. So it's question 1, 3, 4, 5. We'll probably do 6, to be honest, because we've got a big chunk of today's lesson to do that. Well done for listening very carefully there.